Now spring pieces of unequal length. Now we find the spring pieces of unequal length. Suppose if one piece has got length L, other piece might have L0, or if one piece has L1, the other piece is L2. So this fact is to be applied, and the ratio of the lengths will be direct ratio of frequencies. This fact is to be applied. So what is the main context? That is, a spring of force constant K is divided into two pieces, and the length of these two pieces will be L1 and L2, such that L1 over L2 will be N1 over N2. Then L2 will be calculated from this equation. So L2 over L1 will be N2 over N1, and L2 will be calculated by equation N2 over N1 multiplied by L1. This is equation number 1. Now, if L is the total length of the spring, then L is given by L1 plus L2. We have written L1 as it is, but L2 is replaced by N2 over N1 into L1. And from that, we got the equation L1 into 1 plus N2 over N1. But if the same equation is written in terms of L2, then equation will become L2 into 1 plus N1 over N2. The spring constant K of a spring is inversely proportional to length. It means if length will increase, the spring constant will decrease. So if we multiply KL, that will remain always constant. So this constant KL can be written as K1 L1 plus K2 is equal to K2 L2 is equal to K3 L3 is equal to K4 L4 and so on. So the product of K and L will remain constant. So we have mentioned here that KL is equal to K1 L1 equal to K2 L2 equal to K3 L3 and so on. So KL is equal to how much? It is K1 L1. So from this equation we get the value of K1, and that is found to be KL over L1. Now K1 is to be calculated. So what we have done? We have written K as it is, and L over L1 we have computed. So K1 is equal to K into 1 plus N2 over N1. We have simplified the value. Similarly, K2 can be written as, that is, K into 1 plus N1 over N2. So when K1 is to be estimated, then 1 plus numerator is N2, denominator is N1. But when K2 is estimated, then 1 plus numerator will be N1 and denominator will be N2. Now, there are certain examples which are based on simple spring pendulum, and they are all related to simple harmonic motion, or the object which is suspended to a spring pendulum is supposed to be an oscillator. Any particle executing SHM is supposed to be harmonic oscillator, and it follows certain rules as we have discussed earlier. So what are the rules followed? That is, whenever spring is stretched by mass, we will find that displacement increases, and hence the restoring force comes into action, and restoring force will be directly proportional to displacement. Restoring force, acceleration, velocity of harmonic oscillator, all of them will be pointed towards the mean position or the equilibrium position, but the displacement is always away from the mean position. These facts are to be applied in the given example. So there are certain examples based on spring pendulum. Now we come to the main context. Now our question is, length of a spring 2 centimeter increases. Now there is a spring, its length is 2 centimeter, it increases when a body of 1 kilogram mass is suspended from the weightless spring. However, we know that spring has got the weight, but in all our calculations, until otherwise it is specified, we assume that we are taking light inextensible spring. Now length of the spring 2 centimeter increases when a body of 1 kilogram mass is suspended from the weightless spring. So when we suspend 1 kilogram mass, the length becomes 2 centimeter. That is 2 centimeter increases. This body is stretched up to 10 centimeters. That is from 2 centimeter to 10 centimeters. Time period of vibration of spring and the maximum kinetic energy of the spring oscillation will be. So we have to find the time period, which is 2 pi under root m over k. And if it is the frequency, it is 2 pi under root k over m. And my maximum kinetic energy is half mv square, or that is, if we wanted to find the kinetic energy, it is half m omega square y square, or y can be taken as x if it is horizontal displacement. So, spring constant, as earlier we have discussed, it is F by y, where F is that force which causes y increases in length. So, F is a restoring force and y is vertical displacement, k is the spring constant. Now here we find that F is that force which causes y increases in length. So F is known to us according to the question. It is given as 1 into 10n. 10n stands for 10 Newton and y is 2 centimeters. That is given as vertical displacement in the first line of the question, and that becomes 0.02 meters. Now from this we will get the value of k by putting F and then putting y. So we are using the formula k is equal to F over y. Put the value of F, put the value of y, and our net result will become 500 newtons per meter. That is the spring constant. After suspension of 1 kilogram body and stretching it, the time period of oscillation will become 2 pi under root m over k, and k we have already calculated. So it is 2 pi m over k under root, it is 2 pi under root, the value of m we have computed, the value of k also computed, and by simplifying, the result becomes 0.28 seconds. So time period of this type of pendulum will be 0.28 seconds. Kinetic energy of oscillation, that will be given by function half kx square. So work done to stretch spring up to 10 centimeters. What we have to do, we'll write half. K will be taken as 500 and 10 centimeter means 0.1 meter. So for x we write 0.1 meter and square it. After calculation, it becomes 2.5 joule. Now in our next question, a body of mass 0.1 kg is attached to two springs. And the force constants of the springs are given 8 Newton per meter and 2 Newtons per meter. That is, spring constants are given means the value of K1 and K2 is given and mass is 0.1 kilogram and supported by two rigid supports. If the body is displaced along the length of the spring, the frequency of vibration will be how much? So here we are taking, that is frequency 1 over 2 pi under root k by m, but k is the total constant, that is k1 plus k2. We put the values and the result will be 1.6 seconds, that is per second. So in the figure it is mentioned 8 Newton per meter and 2 Newton per meters, that is the force constant. After calculation, the result comes to be 1.6 per second. So it is 1 over 6 over second. Now in another question, one body of mass m is suspended from 3 springs as shown in the figure. Each spring has spring constant k. If mass m is displaced slightly, then time period of the oscillation will be how much? Now normally the time period is given by function 2 pi under root m over k, whereas frequency of oscillation is given by function that is 1 over 2 pi under root, that is k over m. Now the resultant spring constant of the parallel combination. In the parallel combination, the resultant spring constant, that is k dash, that is calculated by adding the two force constants. So force constant or spring constant is the same thing. So we add the two numbers, it will become 2k. Resultant spring constant of the series combination of the spring K and K dash. So if the springs are K and K dash, their total resultant will become 2K. And that is K double dash we have to calculate. So K double dash means K dash K over K dash plus K. Now, we can write it like this. According to the question, K dash is 2K. So, in the equation, K dash is replaced by 2K. And if 2K is multiplied by K, it will become 2K square divided by, and K dash is replaced by 2K. So, the net value will become 3K. So, in the numerator, we get 2K divided by 3 because one of the value of K will cancel off. Time period of system T is equal to 2 pi under root m over K double dash T. K double dash. So this 2 pi m over K double dash. K double dash we have already calculated and that is 2K over 3. So time period is calculated by function T is equal to 2 pi under root 3m over 2K.